that was just a blank recording. All right. Well, sorry about that if you were watching that last recording. Now it's moving. Oh, see, I'm making myself all nervous and stuff. Unit 9, liquids and solids. As opposed to gases, which we already talked about. Gases got their own unit. Liquids and solids, they have to split it. We're starting here with module 22. Which I'm going to lovingly call IMFs. Those of you that did the reading probably know what IMF stands for. Intermolecular forces. Not to be confused with intramolecular forces. And actually, this is a good time to get into the semantics of that all. You all know what that term inter means. You probably use it all the time. How many of you take the interstate? Great. If you take the interstate, you're in theory taking a highway that goes between multiple states. So an intermolecular force is a force that is felt between more than one molecule. The opposite of an intermolecular force would be what? Intramolecular force. And what would be an example of an intramolecular force? Within a molecule. Intra is kind of a weird term. It's not used in a lot of places. And I've found that students here at the community college they're not really involved with the one example that I have of intra being used. But when I was in college, I played intramural sports. That was teams within my college just playing each other. I think the term intramural literally means, I had a student look this up. Was it in this class? No. Intramural literally means within the walls. Mural, like a mural on a painting, a mural on a wall. Within the walls. So intramural sports that are played within the college. Intramolecular forces that are felt within a molecule. Could you give me an example of an intramolecular force? A force that is felt within a molecule. A force that a molecule feels. Covalent bonds. And if we wanted to be a little bit more specific about what bonds, we could describe them. What types of covalent bonds do molecules experience? Like, we've got some descriptions. We've got a lot of descriptions we can put in. Polar, non-polar covalent. There's some other terms that we can use to describe bonds too. Correct. Ionic would not be a good example of a covalent bond. That's a good expansion on a nonpolar bond. Polar and nonpolar and technically pure. But there's another term that we can use to describe covalent bonds. Things that hold together a molecule. What? No, that's kind of, yeah, sharing is the definition of the covalent. There you go. Single, double, triple bonds, but then we have more descriptions that describe the nature of the bonds within double and triple bonds and single bonds. We're going to get to that. That's actually not intramolecular. That would be intermolecular. These are terms, I know this is really, I'm trying to get you to think of the word that's in my head. I'm not doing a good job. Thinking of these terms like sigma bonds, pi bonds. Now, actually, ionic bonds kind of finds itself in a rocky situation here, because we don't really consider ionic compounds to be molecules. We consider them to be compounds, individual ions that are holding each other together. So ionic bonds, yeah, intuitively they fall into that category of intramolecular. They hold that ionic compound together. But then more technically, they kind of fall into intermolecular forces. It is the force that holds different ions together. So ionic bonds finds itself in a weird spot here. We're going to dive more into each of the individual intermolecular forces. But before we do, I want to go back and talk about all of our individual phases. First, we'll look at how kinetic molecular theory defines phases. Do you guys remember kinetic molecular theory? When did we use it before? Yeah, when we looked at pressure. We actually saw that the kinetic molecular theory had to be followed in order for ideal gas law to be followed. Things like gases don't take up space, they don't interact with each other, their collisions are elastic, energy is not lost in those collisions. It turns out KMT doesn't just define solids, but it defines, or just define gases, it defines solids and liquids too. KMT defines solids as tightly packed together molecules. And beyond just being tightly packed, a lot of solids have some sort of crystalline structure. Crystalline here just means it has a regularly repeating pattern of molecules being packed together. You might think of ice, solid water, having a crystalline structure. All of those snowflakes are formed because of the regular repeating framework of the water molecules that build it up. These molecules vibrate but they don't move past each other. So what do I mean by vibrate? Well, we're talking about how gases move all over the place. And those randomly moving gas molecules run into each other. That kind of dissipates their energy, puts it into the next molecule. Well, solids don't have that much freedom. They can't fly around. Instead, they're rigidly packed, but they're still vibrating with energy, just little bits of energy. So think about the solids that make up everything that we're touching, our clothing, the chairs, the tables, your pencils. Those molecules are all tightly packed together, but they're not frozen. They have some amount of energy. They're vibrating to some extent. And oftentimes, it's vibrating inside of that covalent bond. Those bonds are stretching and compressing and expanding, and that's the vibration that those molecules have. An example that I like to give of what solids look like and what their experience would feel like is to draw kind of a pile of bricks. These bricks can't move past each other. They're locked in space. They're kind of in a regularly repeating pattern. And yet they still have some amount of wiggle room. So they're able to vibrate back and forth just a little bit against each other. Liquids we can define as being closely packed. What's the difference? Liquids, although closely packed, don't have any sort of crystalline pattern, and that's because they have some amount of freedom to move around. So in an example that might give you a feeling for what liquid molecules experience, I like to think of a ball pit. Inside that ball pit, you can push those molecules past each other. None of them are flying away. They all stay close together, but you could take this molecule and shove it past any of these other molecules to make it move around. Closely packed, not tightly packed. Closely packed with some ability to move past each other. Gases, as we defined back in Unit 7, are widely spread out. No organization whatsoever, and they move independently other than for their collisions. Now, I feel like coming up with an example of what gas molecules experience feels silly because a good example would be gases. But to make it a little bit larger and a little bit more tangible, I think that we could talk about bubbles. If you've got a little kid here blowing bubbles out of this little bubble maker, those bubbles will be widely spread out. They don't interact with each other. There's certainly no organizational pattern. The only time they would interact is if they collide and bounce off each other. Although we know bubbles, they're going to collide and burst. Okay, the analogy falls apart. That's okay. This all has to do with how strong the interactions are between the molecules and how much energy these molecules have. So inside this unit, solids and liquids, we're going to talk about how you can take molecules that are closely packed and make them have enough energy to move around each other, and take molecules that have enough energy to move around and take them to have enough energy to spread out. All you have to do is increase the energy. We're also going to talk about why different molecules that have the same amount of energy will show up with different phases. That's actually what I want to give you an example of right now. Different chemicals, different phases, same energy. So I'm going to give us this energy plot. You can see that we're going to start on the left-hand side and extend forever to the right-hand side. That means that on the left-hand side, we're looking at a compound that has no energy, and we would measure that temperature as being 0 degrees Kelvin. Remember that we decided Kelvin is an absolute unit. This same temperature in Celsius would be negative 273.15 degrees Celsius. Kelvin says, how can I have some amount of negative energy? Celsius says, well, that's just negative relative to when water has the energy to freeze and melt. Kelvin says, okay, this is a system with no energy. Regardless of the chemical, and I'm going to give you two examples of chemicals here. Regardless of the chemical, everything is a solid here. Water here behaves as a solid. That's not the color I wanted to give water. And nitrogen gas, diatomic nitrogen behaves as a solid. Obviously not a gas because there's no energy. There's not enough energy for those molecules to move past each other. Every molecule has such little energy that it is locked in these places. As we start to increase the energy, as we start to give energy to these molecules of water and to these molecules of nitrogen, let's increase the temperature from 0 Kelvin to 63 Kelvin. At 63 Kelvin, the molecules of nitrogen now have enough energy to move past each other. Whatever intermolecular forces are holding them in place, they have enough energy to move beyond those intermolecular forces. Nitrogen melts. We get N2 liquid. Water also has 63 degrees Kelvin energy, and that is not enough energy for the molecules of water to move past each other. So water stays as a solid. We increase the temperature even more. We get to 123 degrees Kelvin. At 123 degrees Kelvin, the liquid molecules of nitrogen now have enough energy to overcome the intermolecular forces holding them close to each other, and they leave becoming gases. 123 degrees Kelvin, nitrogen boils into a gas. Water still doesn't have enough energy to overcome the intermolecular forces that keep it closely packed together. Water stays a solid. So, true or false? At 123 degrees Kelvin, nitrogen is a gas, water is a liquid. The molecules of water and nitrogen have the same amount of energy. True? They're at the same temperature, and that temperature is proportional to their kinetic energy. Then why is one of them a gas and one of them a solid? They're just showing that energy in different ways. The nitrogen gas is showing that energy largely through translational motion. It's moving through space. It's also tumbling around. Whereas the water is not moving. It's not rotating. The water instead is simply vibrating. So water has more energy here than it did before, which means it's just vibrating more strongly. And that still takes a lot of energy. It's got the same amount of energy as N2. But that energy is being blocked, if you will, by the intermolecular forces. Each molecule of water still has a strong attractive force to its surrounding molecules. There's not enough energy to break free of that attraction. Now, you can imagine nitrogen is going to stay gas for the rest of this. So let's see what temperatures we need to get to change water. 273 degrees Kelvin. What is this temperature in Celsius? 0 degrees Celsius. About 0 degrees Celsius. Water begins to melt. Now we get liquid water. Nitrogen, still a gas. What's the difference between gaseous nitrogen at 123 Kelvin and gaseous nitrogen at 273 Kelvin. It has more energy. It's moving faster. That's the only difference. At what temperature in Kelvin will water boil? Good. 100 degrees Celsius gives us 373 degrees Kelvin. That's when water finally has enough energy to break free of all of its intermolecular forces and transition into a gas. Different chemicals, same energy, different representations of that energy, all caused by the intermolecular forces between the molecules. Before we dive into the forces that actually hold together covalent molecules like water and nitrogen, let's take an easy bite out of ionic forces. The ionic bond strength is directly proportional to the enthalpy of the lattice. Do we remember what that delta H lattice told us? So you're right that delta H lattice applies to things with crystalline structure, that lattice structure. But there was actually an assumption about what delta H lattice meant. What is delta H lattice? It's the amount of energy required, good, for 1 mole of a salt to be transformed into its gaseous ions. Doesn't that sound like a phase change? 1 mole of solid into 1 mole of gas. So the bond strength, what's needed to overcome these forces that hold solids closely together, it's directly proportional to that enthalpy of the lattice. That means that we can say with increasing delta H lattice, we will see increasing melting points and boiling points for our ions. If you don't have melting points and boiling points for an ion, but you somehow have its enthalpy of its lattice enthalpy, well, then you can just make assertions about which ions will have larger melting points and boiling points. What were the factors that contributed to larger lattice enthalpies? Charge. So as the charge increases, you guys, I want to make sure you know what MP and BP are representing here. Good. As the charge increases, what can we anticipate about the melting point and the boiling point of that ionic compound? Also increases. Larger charges, stronger attraction, more energy required to make those ions move past each other, more energy required to make those ions separate from each other. What about the size of the ion? As the radii of the two ions in the ionic compound increases, what can we expect about the melting point and the boiling point? Do you want to try and justify why it will decrease, Blake?
I read it on the
Nice. Good. So we've got this situation again. This is actually just a different version of Coulomb's law. You can see that it's written with Q's instead of Z, and it has K instead of capital C, and it's written as F instead of, I forget what Coulomb's law was written as. I think also C. All we're saying is Q and Q1 and Q2 are the charges, and as those get larger, the force required to overcome their bond also gets larger. But just like Ryan said, as the distance between those two ions increases, you divide by a larger number, the force required to separate them decreases. That's as easy as it gets. That's all for ionic compounds. So should we do some practice problems and try to rank ionic compounds by their predicted boiling points? Let's do it. How about this? You guys have been working with ions all semester long, but I want you to really get familiar with ions. So why don't you dig into your toolbox of ions available to you and come up with an ionic compound. In groups, we'll put them on the board and we'll try to rank those compounds by their predicted boiling points. Because this is already an easy problem, so let's make it as challenging as possible. Okay? See if you can get into 5 groups, so about 3 to 4 people each. Come up with one ionic compound each. Any one ionic compound, but be as creative as you can be. Okay, maybe don't be as creative as possible. If you don't know the charges it takes on.
Oh, Einstein takes on a +3.
How do you know that? Just off the brain. Good job, Einstein. Okay, when you're ready, yell them to me. I'll write them on the board. You got one? Sodium bicarbonate. Awesome. Is that what you wanted? You said the name, is that the chemical formula you were expecting? Or were you expecting sodium carbonate, Na2CO3? That's bicarbonate, HCO3. Okay. So you picked the name, but you didn't pick it, you didn't recognize its chemical formula. This is a good opportunity to practice your ions, right? Okay. Cesium plus 2. Honestly, I don't know that acetate takes on a plus 2 charge very commonly. Is it plus 1? I don't know. I don't say it a lot, to be honest. Oh, it's a halide. Oh, so I had it. So I did have it right. Okay. It's in the halide family. It's just, I don't often see it being reported as behaving like a halide. So maybe it takes on a -1 charge. Maybe it doesn't as often. Not that it can't exist. I'm sure you could find it in some remote part of the universe. Others, you guys have yours in the back? Calcium chloride. Nickel oxide. Good verification, but nickel pretty much only takes on a plus 2 oxidation state. I don't think nickel is one of those ions you need to know Roman numerals for. That's a good reminder, right? Which ions take Roman numerals, which don't? How about you guys? Yeah. Potassium bromide. Cole and Dahlett, you guys did it yourselves? Did you do it yourselves or did you work with them? Sure, but can you give me what charge on copper you want? Okay. Plus 1 or plus 2 for copper. And thiosulfate. Okay, so copper 2 plus with thiosulfate 1:1. All right. How about you guys in the back? Did you guys come up with one? Jacob, Minji, Silver? Okay. Minji and Silver? No? Did you all collaborate? We'll just say you did. Great. Good work. All right, is that everybody then? All right. Not easy, is it? We already did something easy like this last week with our worksheet. We had very simple ions that had very predictable radii and charges. Last week we said that the lattice enthalpy depended on one of these variables more than the other. Charge. So rather than digging into the radii of these ions, and some of these ions really are a lot bigger. Thiosulfate, a polyatomic ion, that's a much larger ion than, say, chloride, bromide, oxide. Bicarbonate, also a bit of a larger ion. So there would be some impact, but if you remember, we saw that fluoride to halide, that radius had some impact on like 300 joules, whereas a +1 to a +2 pair had something like 3,000 joules of a difference. So let's rank these first by their charges. What could we predict to be on the lower end? And we'll just start there. We're not going to have to say the lowest, the highest. What's on the lower end? What's on the higher end? Give me one that's on the low end. Cesium acetate. Astatine. CSAT on the lower end. What else? Potassium bromide's on the lower end. Good. And by the way, that's because we're looking at +1, -1, +1, -1. So we're looking at lower charges. What else has lower charges? There's another pair that has +1, -1. Sodium bicarbonate. Good. Na plus, HCO3 minus. Okay, so those three are going to be on the lower end. Now, can we rank which ones are going to be on the higher end? Copper thiosulfate. In copper thiosulfate, we're looking at copper 2+, thiosulfate 2-. What else? Nickel oxide is 2+, 2-. And what about calcium chloride? Good. So we actually know our middle ground. We've got a +2 and a -1 ionic pair. So this guy should fall right in the middle. Now that we have things separated by the charges that they have, now let's lean into the ionic radii. Remember, let's go from lowest predicted melting point and boiling point, the easiest to separate, up to the highest predicted melting point and boiling point. Which of these compounds is going to have the lowest boiling point? Those pairs that are +1, -1, or those pairs that are +2, -2? +1, -1 should be on the lower end. Now, which ones should have the lowest melting point in that group? Things with larger radii or things with smaller radii? Lower. We're going to go to the very lowest. Larger radii, easier to separate. So which of these has the largest radii predicted? CSAT, because CS is very large, AT is very large. You might also be torn between sodium bicarbonate, because at least CSAT is just 2 nuclei. Sodium bicarbonate stretches across several nuclei. That bicarbonate structure alone is a very large ion. So I'm going to wager, actually, I'm curious. How many of you think CSAT would have the lowest melting point because it has the largest radii? How many of you think CSAT would be second lowest because sodium bicarbonate has a larger radii? CSAT as the largest radii? Sodium bicarbonate as the largest radii? Unsure? Good job. All right, I think we're split, but honestly, I think I saw more hands for CSAT. I would wager the opposite, but let's go with what you guys want to see. Actually, I'd love for you to Google all of these, and we'll put them up there. All right, now we've got potassium bromide, which is the only one left in this. Potassium bromide, not really small ions, but relative to these other two compounds, smaller radii. Then we said calcium chloride falls right in the middle because calcium chloride is a +2 with a -1 ionic pair. Now what about nickel oxide and copper 2 thiosulfate? Which of those would have the highest boiling point, the hardest to rip apart from each other? So all of that and it wasn't even recording. Bummer. At some point, I had plugged this in. It got very hot. The little receiver is charging my computer, so the receiver gets hot. And then I unplugged it. I don't know if you guys heard my camera like ding, ding, ding. That's the noise the camera makes when it connects to the software for the video. And it had paused the recording when it did that, which meant I made this announcement twice. And you know what, though? It only matters for you guys. It doesn't matter for the online classes. The online classes don't have to do the ACS exam. But the online classes didn't get real chem for free either. So this is the trade-off. You have to take the ACS exam. You got real chem for free this semester. You all got 8 Real Chem for free, right?
Yeah.
Good. Nobody paid for it. Good. All right. Why don't we dive back into this? And let's take a look at how intermolecular forces show up for covalent compounds. Do you all remember the analogy that I made about chemicals and matter early on back in the beginning of the semester? I said that chemistry can be thought of as just the study of magnets, and all of these chemicals are really just magnets. And those ionic compounds that we ranked and somewhat correctly predicted their melting points, they're really just very strong magnets. Other chemicals are very weak magnets. Covalent compounds experience a range of forces, and those forces go from basically very, very weak magnetic attractions to very, very strong magnetic attractions. Here are the terms that we are going to be looking at. Dispersion force is the weakest type of force. This is the force that is present across all matter, no matter what its nature, but some chemicals only have this force, which means they don't interact with other molecules very strongly at all. Dispersion force is also called induced dipole, and it's also called van der Waals. You guys might recall van der Waals is the name of the equation that we used for non-ideal gases. Because at high pressures and low temperatures, molecules start having attractive interactions with each other. Those are van der Waals forces holding things together. So the same deviation from our gas law is the result of an intermolecular force. The next strongest interaction is called dipole-dipole. This is an attraction where one dipole's partial negative and partial positive lines up with another dipole's partial positive and partial negative. And remember, partial positives, partial negatives, those are not true formal charges. Those are not ionic charges. So it's really just, there's a little bit of extra density here of electrons, a little less electron density over here, and those little extra, little deficient densities in electrons allows for these partial positive to partial negative attractions. These are at least always present, whereas dispersion forces, or in other words, induced dipoles, those happen for an instant and then they disappear. That's the idea of having something that is made of magnetic things that can create a very small magnetic attraction for a second, and then it goes away. Dipole-dipole, always constant, always a stronger force. And then we have one that stands out from the rest, and this is hydrogen bonding. It stands out from the rest because of its name. It's not a bond. It is an intermolecular force. It is an attraction between molecules, but it's named as a bond, even though it's not intramolecular, holding actual atoms together as a covalent bond. And a bit of a misnomer, the hydrogen bond is is actually just a very specific, very strong dipole-dipole force. But because it's very specific and very strong, we recognize it as something else. So let me ask you this. Do you think the strength of a covalent bond impacts the strength of its intermolecular forces? Last week we looked at enthalpies, and we had tables of enthalpies. So for instance, here I've got the HH bond, which had a bond energy of 436 kilojoules per mole, compared to the CH bond at 415 kilojoules per mole. Do you think that having an HH bond in a molecule, as opposed to having a CH bond in a molecule, has any impact into the strength of its intermolecular forces? The intramolecular force, holding atoms together by covalent bonding, does that extrapolate to the intermolecular force between molecules? Why would it? An energy that's required to break two atoms apart and remove them from their bond doesn't have anything to do with electrostatic forces between molecules. In fact, if you have HH in a molecule, that's the molecule. It's hydrogen bonded to hydrogen. That's just H2. H2 has very weak van der Waals forces only. If you have CH in a molecule, there's a range of different compounds you could have, all the way from non-polar organic compounds to very polar organic compounds, which means that this can have very strong dipole-dipole forces with neighboring molecules. Despite being a weaker intramolecular force, it doesn't mean anything about the molecule at large's intermolecular force. Not dependent on intramolecular forces. All right, so let's talk more about dispersion forces. Dispersion forces are the one intermolecular forces felt by everything. Yeah, I kind of forgot. Also, sometimes it's called London dispersion forces, named after the guy London that proposed them. So I want us to imagine two molecules. I'm just going to draw them as these representative circles. And let's say that these are both non-polar compounds. That means that there is no region on the molecule that is more negative, no region that is more positive. There's no partial charges. And yet, at any given instant, the electrons may occupy a region further away from the nucleus, creating an instant of partial positive and partial negative around this molecule. And on this opposing molecule, we may see something similar. The electron cloud sits a little bit further to one side of the molecule, creating partial negative and partial positive, allowing for this attraction. And in the next instant, the electron clouds shift. And this temporary dipole that has been created is destroyed. That's a very weak interaction. It's a non-permanent interaction. This leads to very weak interactions. Here's one way that we can increase dispersion forces. With increasing size, the dispersion force increases. So let's look at some nonpolar compounds that have different sizes. A great family to explore here are the halogens. F2, Cl2, Br2, and I2. All nonpolar compounds. Truly, the only bond there is a pure bond, very nonpolar. And yet we have very different sizes. If we were to try and show the size of fluorine to fluorine interactions, take, for instance, these three fluorine atoms. These three fluorine molecules. And now let's compare that to iodine. Iodine molecules are much, much larger. With larger size, you increase the probability, the statistics of those electron clouds creating permanent temporary dipoles and inducing a dipole. This has very little area for any interaction to actually occur, whereas in iodine, we have a much larger area where interactions can occur. If molecular iodine, I2, has stronger intermolecular forces between its molecules, then which of these compounds has the highest melting point? Iodine has the highest melting point because it has the strongest intermolecular forces. Or let's take, for example, the phase of matter that you would find these chemicals in at room temperature, 25 degrees C. Fluorine has such weak interactions with other molecules that at 25 degrees C, fluorine is a gas. Chlorine is also a gas. But for that same temperature, for the same amount of kinetic energy, bromine holds on to other molecules of bromine more strongly. Bromine is a liquid. And iodine, for its size, holds on to other molecules of iodine much more strongly. Iodine is a solid at room temperature. All we have here are very weak intermolecular forces, weak van der Waals. But it scales with size, and so we change the energy required to change phase, and our different halogens have different phases. The other way that we can increase dispersion force is with increasing surface area. That might sound a lot like increasing size. Iodine is a much larger molecule. It has a lot more surface area than fluorine. But here, we can actually talk about compounds that aren't necessarily in the same family, like these halogens, simply changing by the amount of size the atoms take up. We can actually look at a different set of molecules. So I want to look at structural isomers. These two chemicals have the same chemical formula, but they're bonded in different ways. The first one is a carbon chain that is 5 carbons long, and the second is a carbon chain where 4 of the carbons all connect to a central carbon. Same chemical formula, C5H12. Different structure. And which of these do you think has the strongest surface area, or the largest surface area? This is called pentane, and this is called neopentane. Pentane has more surface area? Anybody else want to wager a guess? Do you guys agree pentane has more surface area? It can be a little hard to judge, right? Here's one way that I like to visualize this. First of all, these are organic structures, so we can actually simplify them. We use bond line structures to simplify where the carbons and hydrogens are. And so we can just draw these lines to represent carbons, and then recognize there's enough hydrogens at the end of all those lines to satisfy the octets, to get carbon to have 4 bonds. So here, there are interactions between these 2 molecules of pentane all the way along this structure. When I draw another molecule of neopentane, first of all, let's recognize that neopentane is a tetrahedral center, which means that we can look at, from this central carbon, we can see some of the way that it takes up space, its stereochemistry. And here's the interaction that those 2 molecules have with each other. Simply by drawing them out, we can see pentane has a lot more space for interactions with other molecules of pentane. Neopentane has a lot less space for interactions. Now that we've simplified neopentane, you might agree with me that neopentane has kind of a spherical structure, while pentane has a lot more of a sheet-like structure. And so the way that I like to make this make sense, you can memorize this: increase surface area, increase the dispersion force for nonpolar compounds. The way that I like to make sense of this is to compare something a little bit more tangible. Take something like a basketball and set it up against another basketball. Now imagine that those basketballs have Velcro on them. That is that weak intermolecular force. They can stick to each other, they can be ripped apart pretty easily. The only place that these basketballs will be able to connect is just right on that point. Yeah, very little, a very small amount of the basketballs actually touch. Cut these basketballs open, and you can get something like these sheets. Stack those cut open basketballs next to each other. Still have all that Velcro on the outside of the basketballs, and now you have a lot more surface area to Velcro these 2 pieces together, to stick these 2 molecules together. So, dispersion forces, 2 factors, size and surface area, very much hand in hand. Our next intermolecular force is the dipole-dipole. Not every molecule experiences dipole-dipole. this requires having a polar molecule. If the molecule is not polar, it cannot experience dipole-dipole interactions. But if your molecule is polar, this force is much stronger than dispersion. So I want to give you guys a few molecules to compare. Let's look at hydrochloric acid, water, molecular iodine, molecular oxygen, hydrogen cyanide, oh, I'm trying to think of one more. Nitrogen dioxide. Underneath, let's list whether these have both van der Waals and dipole-dipole or only van der Waals. Are there any chemicals in this list that don't experience van der Waals forces? Everything experiences van der Waals. So we could say up here, everything has at least dispersion forces, van der Waals forces. I apologize for switching back and forth between them. It is just so common that you hear both of those names, van der Waals forces and dispersion forces, so I want you to be familiar with both of them. What would rule out a molecule from not having dipole-dipole listed with it? It would be what? It would be non-polar. So are there any that you can look at right away and say, definitely non-polar? Iodine and oxygen. So for iodine and oxygen, that's it. Those are the only forces that those molecules experience. Weak dispersion forces. There's not a lot that holds those molecules together. Are there any that you absolutely know have dipole-dipole forces? Absolutely know that they are polar molecules without having to draw the structure. Water and hydrochloric acid. Hydrochloric acid was one of our first examples of a dipole, I believe. We said hydrogen is not very electronegative, chlorine is very electronegative. So electrons are pulled towards the chlorine, creating a partial negative region and a partial positive. So this definitely experiences dipole-dipole. And I'm going to label that as dip-dip, dipole-dipole force. You said that you also know water is polar. And maybe you're not confident on that right away. We've talked about it a lot, but you could draw out its structure and look for that polarity as well. This is a good time for us to review. How do you know if a compound is polar by looking at its Lewis dot structure? Some tips that we gave back in that unit. Cole? So if there's symmetry in the dipole arrows, they cancel each other out. So we're looking for lack of symmetry to some regard. So one of our rules was, first, the compound must have polar bonds. If the compound does not have polar bonds, there is no way that it has a dipole moment. Then we say that if there's a lack of symmetry somehow, like if there is a way that you could cut through the molecule and see that those dipole arrows never cancel each other out. There is another tip, another trick for looking at a structure and deciding whether it was polar or nonpolar. Lone pairs on the central atom usually indicate some sort of lack of symmetry. If you have lone pairs, that means that you will have a geometry, a molecular geometry that does not equal the electron geometry. So you will have regions on the molecule that have lone pairs, regions that have bonding pairs, and if those bonding pairs are polar bonds, then you will have some sort of asymmetry in the molecule, and you'll have a dipole moment. So when we look at water, we know that water has lone pairs on the central atom and polar bonds between H and O. So we know water is a polar molecule. Water experiences dipole-dipole. What about the HCN molecule? How do we know that it has polar bonds? Is HC polar? HC is non-polar. CN triple bond, is that polar? I know, right? You know how to calculate it? Take their electronegativity numbers, take the difference, and if the difference in electronegativity is greater than 0.4, it's polar. Difference in electronegativity between H and C is 0.4, nonpolar. The difference between C and N is 0.5, polar. So HCN does have polar bonds. There is no lone pair on the central atom, but there's also a lack of symmetry. Carbon is bonded to nitrogen and hydrogen, and those are not symmetric to each other. Polar bonds, lack of symmetry. This is a polar molecule. It points towards the nitrogen. That means that hydrogen chloride does experience these dip-dip forces. What can you say about nitrogen dioxide? Nonpolar? Do we need to draw its structure? Is this a skill that you thought you were done with? Electronegativity, yeah, oxygen is 3.5 and nitrogen, I believe, is 2.6. Yeah, a difference of 0.9. But what about the structure? What if it's linear? NO2 on the left, in double bond on the left, double bond on the right. What if it's a linear molecule? Let's draw it. What atom goes in the center? I'll bond to each oxygen once. I should have 5 electrons from nitrogen, 6 electrons from oxygen twice. 6 and 6 is 12, 12 and 5 is 17. I've already used up 4. 4, 6, 8, 10, 12, 14, 16. Remember, I like to give lone pairs to the outer atoms because they're more electronegative, so they're likely to hold those lone pairs anyways. I ran out of electrons all but 1, and I filled the octet on my outer atom, so I'll add this one last electron to nitrogen. The last step of building Lewis structures was to try and create octets to the central atom by moving lone pairs to be double bonds and triple bonds. Now I can't move more than one lone pair. Nitrogen currently has 5 electrons. 2 more electrons, it's at 7. 4 more electrons, it's at 9. It can't have 9 electrons. That breaks an octet. So I move one lone pair. It doesn't matter which oxygen shares because it would be the same in either direction. There are 2 resonance forms of this molecule. Did that answer it? Why? There's not a lone pair, but there is a non-bonding region. Exactly. There's a lone electron, which means there will be some lack of symmetry. This molecule is not linear. This molecule is bent. And because it's bent, if I tried to draw a plane of symmetry here, I can see that one lone electron on the top of nitrogen is not symmetric with 2 bonds to oxygen on the bottom of the nitrogen. There is a lack of symmetry. There are dipoles that point towards the oxygen. This is what Cole was getting at, which is my dipoles don't cancel each other out. They actually sum together to a larger dipole. NO2 is polar. NO2 experiences dip-dip forces. All right. One more that I want you guys to do in your groups. Carbon dioxide. Van der Waals and dipole-dipole, or just van der Waals? I'm only going to let you work alone for like a minute, so if you need that time to draw your structure, that's okay. But then I'm going to tell you to talk to each other. Get it? Got it? What's the answer? So, how do you know it's nonpolar? Linear, with equal bonds in both directions. You guys decide? Yeah? How about back row? Do you guys want to talk with each other and see if you agree on your final answer? You guys agree? What'd you decide? Okay. Good. Now see if these guys agree. What'd you decide, Jackson? Does that agree with these two? What'd you guys say?
I was saying that too. I'm saying it's polar. Yeah.
Well, it's 2 against 1, so see if you can convince her to join your side. All right, true or false? CO2 has polar bonds. True or false? CO2 has polar bonds. Ooh. Oh, yeah, that was a stumble, but we got there. The C to O bond is polar. If C to N is polar, which it needed to be for hydrogen cyanide, then C to O is also polar. And if N to O is polar, which it needed to be for nitrogen dioxide, then again, C to O is also polar. If the difference here and the difference here is polar, there's a larger difference between C and O. So CO2 has polar bonds. In the Lewis structure, are there any lone pairs on the carbon? Okay, but you know what? We didn't need lone pairs on the carbon for hydrogen cyanide. So that was okay. to still be a polar compound. Just because carbon doesn't have lone pairs doesn't mean it can't be a polar compound. Does it have symmetry? And by symmetry, I mean not just like one line of symmetry you can draw, but like there's no symmetry you can't draw. It does. CO2 is that linear carbon bonded to two oxygens. So it has symmetry, which means that these dipoles, they cancel each other out. So does it have a dipole? No. Does it have dispersion, dipole-dipole forces? No. The only experience that carbon dioxide feels is van der Waals forces. Great. Good exercise. Okay, the last thing for us to talk about, and we'll pick up here as well on not on Wednesday, on Monday next week after the Thanksgiving break, is hydrogen bonding. I'm going to leave you with just a starter for hydrogen bonding. Hydrogen bonding, H bonding, is much stronger than van der Waals forces and dipole-dipole forces. It's still much weaker than covalent bonding. If you're going to break any sort of a bond first, the hydrogen bond requires the least amount of energy before you break a sigma bond, before you break a pi bond. And it requires very specific alignment of atoms and lone pairs. Now, I've drawn this graphic before. I don't know that it always comes across the way that I want to, so I think I'll draw the graphic once, and then I'll show a different way that you can think about it. When a hydrogen is bonded to either a fluorine, a nitrogen, a fluorine, an oxygen, or a nitrogen, keep in mind these are second row elements that are all fairly electronegative. When a hydrogen is bonded to one of these elements, then it experiences hydrogen bonding to the lone pair on one of those same elements. Oops. Okay, my graphic is a shortcut. You guys agree that one hydrogen cannot be bonded simultaneously to three other atoms? So you can have a fluorine bonded to hydrogen. That will experience a lone pair with the lone pair on a nitrogen, or it would experience the lone pair, hydrogen bonding with the lone pair on an oxygen, or the lone pair on a fluorine. If a hydrogen is bonded to oxygen, then it can experience hydrogen bonding with the lone pair on any of these. These are very specific requirements. The reason that I lay them out this way is because a chemistry professor I had once said, you remember hydrogen bonding when you hold the phone. Here's the phone. These are the only elements and the only lone pairs that create hydrogen bonding. And the hydrogen bond, again, is in the dash. Here's a partial positive because these atoms are more electronegative. And then here are the partial negatives. So this dotted line here is representing the hydrogen bonding. Now, I know some of you know hydrogen bonding. It's very important in biology. DNA is that double-stranded helix. DNA is held together, those two strands are held together by hydrogen bonds. Those are not covalent bonds. They're very easy to break apart. They're just very strong intermolecular forces. Proteins that build your body and your enzymes, those also fold and wrap around and oftentimes have hydrogen bonds that hold pieces of the protein in close proximity to each other. So if you provided too much energy to your body, your proteins would have enough energy to break their hydrogen bonds and they would unravel and not do the functions they need to anymore. And one of the most important implications of hydrogen bonding is in water. Water experiences a lot of hydrogen bonding between other molecules of water. In fact, water, for its weight, 18 grams per mole, has an incredibly high boiling point because of how strong its intermolecular forces are. Water is unlike anything in the universe. Scientists have had an easy time modeling and predicting molecules using computational studies. And water has always been the challenging point because of its weight compared to its intermolecular forces. Hydrogen bonding is a beast of intermolecular forces. It's not like these other two, but it has very specific requirements. When we come back next week after Thanksgiving, we'll talk a little bit more about the implications of these intermolecular forces. Have a good break, guys. I will see you on Monday.